how high harmonics are generated. Right? The important characteristic of harmonic generation versus high harmonic generation is you have a large number of harmonics generated with almost similar intensity, and there is what is called a characteristic plateau region, and there is a cutoff. Now, these high harmonics can be used to generate attosecond pulses. So, in this part of the lecture, I will discuss how these harmonics would be used to generate attosecond pulse trains or an isolated attosecond pulse, and how does one measure. I will try to give you some insight into it, although not all the details. Okay, how are harmonics generated? How is an attosecond pulse generated? Right, it's quite simple. We already have the answer. You have harmonics. Technically, if I do a Fourier transform of this, it turns out that I would get an attosecond pulse. Okay, why is that? If you look at a simple relation between this inverse relation between the width of in the frequency domain versus the temporal domain, right? You see this relation. So, let us say I have a femtosecond pulse, 800 nanometer pulse, and the duration is maybe 2.5 femtoseconds, okay, and this corresponds to a delta nu, okay, the photon energy of about 1.5 eV. Now, if you generate high harmonics, let us say I have a 10th harmonic or a 20th harmonic, its energy is going to be 15 eV. Okay, I am just giving you some approximate numbers. That would mean its duration would correspond to what? Through this inverse relation, 0.25, right. So, I have something, an oscillating frequency, right. I have a radiation whose time period is about 250 attoseconds, correct. Now, I do not have just one such harmonic, but I have many such harmonics whose time period is 250 attoseconds, 200 attoseconds, maybe 150 attoseconds, and so on. As I keep increasing the harmonic order, the time period will keep reducing. Now, if I take a superposition, a coherent superposition of all of these, so this is in the Fourier domain, right. I have some amplitude multiplied by, I am approximating each of these harmonics as essentially a delta profile in the Fourier domain, omega minus 2n plus 1 omega naught. We already discussed why we get only odd harmonics in the last lecture. So, let us say we only get odd harmonics, we have this homogeneous medium, and you have this kind of delta profile in the Fourier domain. So, my Fourier transform is something like the intensity with respect to omega. I have at 11 omega, 13 omega, and so on. Now, I add up all of these and then look at what does this look like in the time domain. It will turn out that you have these kind of short pulses. So, for each half cycle, I have a burst of an attosecond radiation, right. If I want to link this back to that classical model, you see that those trajectories that are from 0 to pi by 2, which is within half of a half cycle, those are the ones that would recombine, right. So, let us see if I can draw a picture. So, if this is the pulse, we need to combine two aspects. One is the ionization aspect and one is the recombination aspect. Now, something that gets ionized here to here, let us say this is my 0 to pi by 2. So, this is what would recollide and give you some ionization, some radiation. Where does it ionize maximum? It ionizes at the peak of the electric field. That is the other aspect. So, therefore, the electrons, the most probable electrons would get emitted at this peak or maybe around this region, right, in this time window, and it is these electrons that would get recollide, that would recombine and emit radiation. So, therefore, a combination of the fact that you have a highly nonlinear ionization process along with the fact that you have recollision within this particular time window means that your radiation is confined to such a small time window. So, therefore, for each half cycle you have an emission of radiation which is chirped, because depending on a particular ionization time you have a recombination time, and given a recombination time I have an emission of a photon at a different frequency. So, within this time window I will have a spread of frequencies, which would mean that I have a chirp, And I also have an attosecond pulse which is basically confined to half of a small portion of half cycle of this driving laser field. So that is how you get an attosecond pulse train, because it happens at each half cycle. Okay. Now if I want an isolated attosecond pulse, what would one do? Technically, if I can generate just one pulse, one driving pulse or 1 or 2 cycle driving pulse, then I would just get only one attosecond pulse out of it. Okay. So now how do we measure it? Okay. Generating the pulse is one thing, because in 1988 when Anheuser had the high harmonics, she in principle had the attosecond pulse, but to be able to show that have an attosecond pulse is an equally complicated thing, and therefore what does characterization of pulse require? You have already done these in your previous lectures. You need the amplitude as well as a phase to be able to fully characterize the pulse. Now for the kind of radiation that we are talking about, now if I have a 10th harmonic 1.5 eV, so what's the energy like? It's 15 eV or maybe 15 to 20 eV or 30 eV. Now is this sufficient to ionize the hydrogen atom? Yes, right. So the way to measure the spectral amplitude or E of omega square is through photoionization. So what you do, you take an inert gas, you photoionize it, and the probability for photoionization with a certain photoelectron amplitude, you can use first order perturbation theory, because you can just ionize it with a single photon absorption. You see that it is proportional to some matrix element square from the initial state to this continuum state and modulated by the spectral amplitude of your pulse. So if I have a known system where this particular transition matrix elements are very well known, then I measure in the experiment what is this probability P of k, right, that is photoelectron spectroscopy, and then I can back calculate what is my spectral amplitude in the pulse. So this single photoionization experiment would be able to give you what is the spectral amplitude, which means you will also be able to find out what is the mean position. So that means I have some photoionization spectra that looks like this. P is a function of the momentum or the energy of the photoelectron, and you would see that you will have a certain peak, which is a broad peak at certain photoelectron energy, and the peak would correspond to h bar omega minus the ionization potential. Okay. So from this you can back calculate what is your central frequency as well, and you will also get some estimate for what is the duration, because from this. Now what if I want phase as well? So this is a much more difficult question. So in elementary optics, right, if I want phase information, what would you do? You would need to do interference experiments. Now you need to do an interference here, but not with an absorption or an emission, but you would need to do interference in terms of photoelectron spectroscopy, because the messenger is the photoelectron. You are doing a single photoionization. So what one does is, this technique is called the rabbit technique. So what one does is do a photoionization with a mixture of this attosecond pulse train plus the infrared. Okay. So if I have the attosecond pulse train, I have a number of harmonics. Each of the harmonic, which is the delta pulse, would give you a peak, right. So let us say I have the photoionization due to some ith harmonic. So let us say that is 11th harmonic. So this is 11 h bar omega minus ionization potential. Okay, the axis is the same. The probability of finding the electron at a certain moment or energy versus the energy. So I will just maybe write this as P of E, that is a photoelectron energy. When it gets ionized by 11th harmonic, I get such a peak which is at 11 h bar omega minus IP. When it gets ionized by 13th harmonic, I would get a peak 13 h bar omega minus IP, and so on. I will get a series of peaks corresponding to each of the harmonics. Now when you have also an infrared present there, you can have an additional transition. This would correspond to the following. So that is the ground state of the system, that is a continuum, and let us say these are the continuum states into which it gets populated. Now you can have what is called a continuum transition, which means it is already ionized, but then it can further absorb another photon, right. That means it absorbs another photon at h bar omega. This is 11 h bar omega, and instead of having photoelectron just at 11 h bar omega minus IP, I can also have a photoelectron which is being emitted at 12 h bar omega minus IP. So this is what is usually referred to as a side peak, because with the attosecond pulse train you would only get at n plus 1 h bar omega minus IP. Now this additional photon with this IR frequency means the electron which is at this photoelectron energy can absorb one more photon and then get excited to some other higher continuum level, and you get a photoelectron at 12 h bar omega minus IP. Equivalently, you can also have an emission process. An electron which is at 13 h bar omega minus IP can emit stimulated emission with this incident h bar omega, and then also lead to a peak at same 12 h bar omega minus IP. So I have an absorption as well as I have a stimulated emission from 13 h bar omega minus IP to 12 h bar omega minus IP. Now I have two pathways, this absorption process and this emission process, both giving a photoelectron at the same energy, and these two pathways would interfere and give you some characteristic time scale if you look at the interference pattern, and that will let you extract phases. Okay. So this is an interference with the help of photoelectrons. Yeah. So the first process is that an absorption of 11 h bar omega and an absorption of h bar omega. The second process is an absorption of 13 h bar omega and a stimulated emission from there with the h bar omega to give a final state with the same energy, right. So there are two pathways giving you a photoelectron with the same energy, and these two quantum pathways would interfere, okay, and this is the interference with which we will try to extract the phase.
So stimulated absorption or emission always have to be h bar omega, or could it also be some other?
No, because you are explicitly using an attosecond pulse train along with an infrared, which is what it originally generated the attosecond pulse train. So that's why you use this. And experimentally it's much easier because in the same setup you have both the laser fields which you can control the delay.
When you say IR, it is the driving laser.
Driving laser, yes. Okay, so now this is how a typical experiment would look like. So what one does is, I have an attosecond pulse train, you have an infrared pulse. So let's say your infrared pulse, and you have an attosecond pulse train. So I'll try to draw this as simply peaks like this. Okay, these are the attosecond pulse trains, and let's say in your experiment you have a way to control the delay between these two, right. If I control the delay between these two, I can do the same experiment multiple times with different delays. So what you see here is the delay axis, and this is the photoelectron spectra. So again, just like how I showed these probability distributions with the quantum mechanical simulations. So let's say at the 0 delay, if I want to know what is the photoelectron spectra, I need to cut across this and then find out what is the intensity as a function of this kinetic energy. The color code includes what is the actual value or the probability, and you see that, and that's how you compute, sorry, just something fell now. So now you do the same experiment, do the photoelectron spectroscopy but with different delays, and you see that these side bands, these are the side bands that come up, oscillate, right, the intensity oscillates. So there is a certain maximum value, it goes back to 0, and then it goes back to certain maximum value and goes back to 0. And this is a beating. So if you plot this, so you see that you have, as a function of delay, the intensity kind of oscillates from certain maximum to a certain minimum. Now if you use second order perturbation theory, right, I have not do the calculation because it's a 2 photon process. There is one XUV photon or one harmonic photon, that's 11 h bar omega or 13 h bar omega, and one IR photon. So it's a 2 photon process that we are having, an ionization with absorption or an absorption emission of 2 photons. So therefore you can use a second order perturbation theory to calculate what is the probability. And if you do this, you find that this side band would oscillate in the following fashion. So, the oscillation frequency is given by this omega naught, which is the driving laser frequency. So, therefore, you see this is an infrared laser pulse with a time period of about 2.5 femtoseconds. So, that is what is shown here, starting from -2 to +2, and you see that it oscillates as per this driving frequency. I see 3 maxima, right, which corresponds to this oscillation in the driving frequency. Now, you also see that there is an overall phase shift, right. This is an overall phase shift. There is something that is coming from the atomic transition matrix element, and there is also something coming from the actual harmonic. Okay. Now, let us say I assume that I take a certain system where this particular atomic phase, which is related to the dipole transition matrix elements, is exactly known. So, phi atomic is known. Now, what is unknown is the difference between phi 2k plus 1 minus phi 2k, and that is what you can extract from the spectrogram. Okay. Now, I cannot exactly get a phase from one particular oscillation, but if I compare two different oscillations, that means let us say in this figure I compare 10 and 12th sidebands, I can look at the phases, take a difference between them, and I will be able to compute. So, let us say this 10th sideband would give me phi 12 minus phi 10, right. It has that phase information, whereas the 12th sideband has the information phi 14 minus phi 12, right. Now, I can use these two, subtract and divide by the appropriate time delta t, and then what you get is the second derivative of the phase, right. If you look at this approximate formula for a derivative, it is the difference divided by a delta t, right. If I want the second derivative, it is such a thing, delta phi 14 minus, if I take a difference of these two, I would get delta 14 minus 2 delta 12 minus, phi 14 minus 2 phi 12 minus phi 10. If I divide it by delta t square, I would get the second derivative. So, therefore, by comparing two different sidebands, I can get the second derivative of phi, and if I want to fully characterize the phase, I need, you have all, I think you have looked at it this in different earlier lectures, the phi which is a function of t can be expanded. You can write this as some constant phi, the first derivative of phi with respect to time, which is the instantaneous frequency, and you can also have of course times phi minus phi naught plus the second derivative and so on, right. So, what this particular approach where you have this two photon interference gives you is the second derivative, right. You already get d phi by dt from your photoelectron spectroscopy, you know what is omega, right. Now, you also want to know what is the second derivative, which will give you the linear chirp term. So, this is how you characterize the wave, the attosecond pulse train a little bit more, but it is not a complete characterization, because a complete characterization would require all higher orders. But at least we get some estimate of the chirp, because we know that the attosecond pulse is a chirp. That is what our classical model tells us. Okay, any questions? I can pause here. That comes out of second order perturbation. I can show you the calculation, but not for this lecture. It just, it will look like what we did in the first lecture, like yesterday, where I had done some second order perturbation theory, right. You will do the same thing, but now you have the final state being a continuum state.
It looks as if the consecutive harmonics are out of phase by for the negative sign.
Yeah, maybe one has to remember, have to check the details, but yeah, you get such essentially an interference which gives you this. Yeah, anything else? Yeah,
Can electrons
please.
also absorb neighboring fields that are emitted? Earlier we were discussing about how 13 H cross omega and 11 H cross omega will interfere.
Yes.
But can a given electron interfere with, absorb the harmonic of another electron? Does that also?
What is meant by?
The recombination of two different electrons releasing two different.
So you have to think about this as like two different experiments. Again, we missed it. That is, you don't have a strong laser now. So your driving laser is not strong. That means, so originally when you generate high harmonics, your infrared is strong. But when you do this rabbit experiment, you want this electron to just absorb one photon. It's already in the continuum. It's a simple photoionization process like thing where it just needs to absorb one photon, and it's easily allowed. It's already a free electron. It will pick up this electron. So therefore, the IR that you combine with the attosecond pulse train is weak for one to be able to use perturbation theory. So therefore, this IR is not going to generate high harmonics. It's a very weak field which is just tweaking your system. So therefore, in this second experiment where you already generate high harmonics, and now in order to characterize it, I have a new setup where I photoionize a system using the generated high harmonics. There is no probability that this IR will actually generate harmonics.
I meant in the continuum state of the electron, can the electron absorb the harmonics from other electrons?
No, I'm confused.
Yes. Once the electron goes into the continuum state,
Yes.
can the electron now absorb the emitted harmonics of its neighboring electrons?
Neighboring electrons. No.
Which have again recombined, but now
No, there is no recombination that's possible here. That's what I'm saying.
where is it not?
In this particular experiment, so the first part is like you have some gas chamber. Let's think about it experimentally. You have driven a very strong laser into that, and you got harmonics. Let's say your field strength is like 0.05 or 0.06. Now when I do rabbit, that's now the generated harmonics are brought into another chamber where I do a photoionization experiment. This is not strong field ionization. This is a simple photoionization experiment where you bring down the intensity of the infrared laser to very weak field. It's maybe 0.01 or 0.005, where it can just do a little photoionization. It can create one little transition. It is not strong enough to actually ionize a bound state, but it can do a continuum. So this weak field now that enters a new chamber cannot actually generate high harmonics. So there is no neighboring electron that is generating you high harmonics. I have generated high harmonics, I am now in a new chamber. I have brought down the infrared laser intensity to a very weak field, which will just tweak your system. Is that okay? Yeah.
But in that case, there will be MPI possible for the weak field IR to ionize the new species. Where is it? That's also possible.
No, the IR cannot ionize the sample because you have 13.6 eV as your ionization. You will need a many photon process to be actually ionized. If you shine an infrared laser on hydrogen atom, it does not do much unless the field strength is very high. Okay, but it can do something to an already ionized electron. If I have an already ionized electron, it can create this second transition, but it cannot do much to the bound state when it is weak.
That way, the delay is important because the high harmonics are already, since it's very high energy, it can ionize, for example, the hydrogen atom, and then you have the electrons in the continuum already there. That's where the IR will come at a certain delay and then cause the continuum transition.
Right, yes. And now as you change the delay, you see that the intensity of the side peak changes. That's because you have these two different pathways, and the IR modifies these two different pathways in a slightly different way, and therefore you get an interference. Okay. So one needs to, for example, compare with, let's say, Michelson interferometer. Right? Let's say I put a wedge in one of the arms, right? And I keep moving the wedge. As the optical path length keeps changing, and I see that the fringes keep changing. Right? So it's something like that, but you're doing with the photoelectron. So your infrared laser is going to do some modification to your pathway, one of both the pathways here, but its modification to these two different pathways is different because one is an absorption, one is an emission. And depending on the delay, I have a slightly different modification. They both add up, and then when I scan through the delay, I see this kind of an interference, and quantum mechanics tells us that this is the kind of modulation that one sees, and from that modulation one can extract the chirp.
Just to be clear, so
Yeah.
your delay infrared is completely separate from the driving laser, right?
You take the same driving laser because you can synchronize it, but then you have to bring down the intensity.
But wouldn't that affect your harmonic generation at all?
No, it's already done.
Okay.
So let's say it's done because the entire IR is not absorbed, right? It's a very small process. Now it still comes out of the chamber, and then now you can have a delay arm or something which affects only the IR, and yeah, put an attenuator and so on. I am just sticking to physical principles first. Okay, so now if I want to generate an isolated attosecond pulse, as we discussed in the context of the first slide, you need a single cycle or 2-cycle pulse, and then you get a single attosecond pulse. Now one important thing is to notice, when you have a single attosecond pulse, its Fourier transform does not have harmonics. When we talk about harmonics, what one has in mind is that I have a delta-like behavior at, let's say, 11 h bar omega, at 13 h bar omega, and so on, right? I have clear peaks in the harmonic spectrum. But now if I have a single pulse and I do a Fourier transform of it, it will span the same frequency window. Let's say this is my plateau region. It will still span the same width, but I don't have clear peaks. It becomes a smooth function, right? So that's one important point to note, that when I have a single attosecond pulse or an isolated attosecond pulse, I do not have harmonics. I have electromagnetic radiation spanning the same window, but I don't have specifically harmonics. Okay? I have a broadband pulse. Now how do I characterize this? So therefore, if I have a broadband pulse, I cannot use this 2-photon interference technique, because when I do photoelectron spectroscopy, so I go back to this slide, instead of having these individual peaks in the photoelectron spectra, I'll just have a large blob there corresponding to the bandwidth associated with this isolated attosecond pulse. Now I cannot create these side bands. There is no side band, or there is no empty region in which there was no photoelectron to start off. I have photoelectrons at all this energy range. So therefore I need a slightly different technique to be able to characterize the isolated attosecond pulses. And this technique is what is called streaking technique. And the principle of this streaking technique is follows. It's like our classical model that what we have done. Once the photoelectron gets ionized, you look at what is the energy or what is the modification to the momentum in the presence of an infrared laser pulse. So you set up your Newton's equation, dp by dt is the change in the momentum is minus EE, and electric field is related to this vector potential dA by dt. So if the electron at certain time t prime gets emitted with some photoelectron energy P naught, which is the photon energy minus ionization potential, that's your P naught. At the end of this streaking laser pulse, so let's say this is my driving infrared laser which I am using along with the isolated attosecond pulse. Let us say it gets ionized at this instant of time. Now it picks, when the laser pulse gets over, it picks a certain additional momentum which is A of t, that's at the so for example I want P at infinity at large time once the pulse gets over, then this formula would tell me that it is P at t prime, which is the initial P naught, plus E at minus E at E times A at t prime, because A at t is equal to infinity is 0, the laser field is over, so there is no vector potential. So what has got emitted at photoelectron energy P naught will pick up some additional momentum due to this field, and it gets modified by this P naught minus A t naught, okay, and this is called streaking. Now you have this broadband pulse, and you again delay, you scan through the delays, and you see that if initially I have a blob like this in my photoelectron spectra, this blob keeps shifting as a function of time. So let us say at some initial time I have photoelectron spectra like this, which is spread over 25 to 35 eV in this particular example. As I scan through this infrared pulse, this blob keeps shifting. See, something that is here got shifted to something like this, right, at this particular time delay, because the whole momentum is getting modified by the vector potential at the instant of ionization, and this is what is called streaking. So now from this streaking spectrogram, it is possible to now analyze. So now I don't just have simple photoelectron spectra, which already gave us a spectral amplitude E of omega square, but I also have some additional slices of information which is at given instant of time, how does my photoelectron gets streaked. It will also have geometric effects because it depending on which direction the electron gets ionized, the photoelectron momentum gets shifted. For example, if my photoelectron gets emitted in this direction, but my streaking field is in this direction, then the momentum does not get shifted, right, because it's in a totally different direction. Whereas if my photoelectron is in this direction and also my polarization in this direction, then it gets shifted because my classical equations of motion are component wise, correct. This equation that I have written is for each component. Now if I have a photoelectron that gets emitted with x direction and my vector potential is also in x direction, then I can have this shift in the momentum. But if the photoelectron gets ionized in x direction but my polarization in the y direction, then I will not have any streaking along that direction. So now you can put together all this information and write down a reconstruction algorithm which will be kind of involved, and from there, because now I have more information, I should be able to again reconstruct the chirp information, okay. And this is what is called Attosecond streaking technique. The underlying principle is that the electron picks up some additional momentum depending on the ionization time. Okay. Yes, so that's all I wanted to tell about the generation of attosecond pulses and how do you measure, give a feel for how one would measure, especially the chirp. So attosecond pulses are generated if you have a many cycle driving pulse, right, and if I want an isolated attosecond pulse, I need a few cycle driving pulse. Attosecond pulse train can be measured using what's called rabbit. It's a reconstruction of attosecond beating with two photon interference, right. We had a scheme where you had two pathways and they interfered and you got chirp information from there. And in order to measure isolated attosecond pulses, you do what is called streaking. Now if you want to completely characterize this pulse, there are some advanced methods which is called frequency resolved optical gating. What you do is have some complicated waveform and I want to analyze this. What one does is something like a window Fourier transform. If I can somehow optically gate this in my experiment to this window and then I slide this window through this whole pulse, smaller windows, and do the same kind of a Fourier analysis to this optically, for example using a grating, I now have a higher dimensional information about this pulse, and from that higher dimensional information I should be able to construct an algorithm which would tell me what is a pulse, and that is called frequency resolved optical gating techniques, and there are different techniques to be able to do this kind of gating. Okay. That will not be covered in this course. Okay, so that is for how do you generate attosecond pulses and how do you characterize them. So if you have any questions. Yeah, again it cannot give you a momentum if it gets ionized here. If it starts off and sees the complete pulse, then it cannot give you a momentum boost. If it gets ionized during the pulse, then it will get a momentum boost. Yeah.
Gating you mentioned in the last slide.
Yes.
Over in the frequency.
You can have different kinds of gating techniques in frequency domain, and you can put a nonlinear crystal, you can have polarization gating. There are a lot of methods which Shiva is an expert in that, he can discuss.
So this momentum boost, it also happens when you have multiple attosecond pulses also, right?
When you have, yes, you will also have there, but now you need to tune your intensity in such a way that will become a smaller effect. So what happens in rabbit technique, in this particular technique, is you keep the intensity of the IR very low to be able to induce this transition. The more important aspect of the process you want is a sideband, okay, you do not want momentum shift. Whereas in the streaking experiment, you will still try to keep your intensity of the air pulse somewhat significant, still not to be able to generate high harmonics, but somewhat significant to be able to see some momentum boost, because that is where you have the information about the pulse. Okay. It is about what is your intensity of the IR pulse. In the rabbit technique, you keep it quite low to be able to use a first order and second order perturbation theory, because you have clearly an empty space where you are creating a new photoelectron and you can analyze what's happening in that empty space. That's the sideband, or where your even harmonic would have actually ionized the system. Whereas here you don't have empty space, right? You have a complete distribution of photoelectrons in that window. Now I should be able to create that momentum boost. Therefore, I need some intensity which will be able to create a measurable momentum boost. Now, depending on the bandwidth of your pulse and what do you mean by measurable momentum boost, you look at what should be the vector potential of your streaking pulse and then set an intensity accordingly. Okay. Any other questions?
I had a doubt in the earlier part where
Yes.
said we use symmetry arguments to prove that even harmonics are not. But that argument was on the assumption that P changes when E changes. P changes sign when E
Yes.
changes. Why is that?
Yeah, that's what you would expect, right? That if I have electron cloud, let's say the proton is fixed, it's heavy. When I have field in one direction, it gets attracted in a particular way. And then when the field is in the other direction, it should get attracted in the other. That's
Since when there is a linear relationship with P and E.
no, even when you don't have non-linear relation, you have basically it has to follow the direction. When you say non-linear relation, you're just saying that whether it's directly proportional to E or E square or E cube or so on, but the directionality is something more fundamental. The induced dipole moment has to follow a certain direction given by the electric field.
But the magnitude can
The magnitude will be different. So, any other questions? Okay, so that's all I wanted to tell. Right? If you have any questions in any of these 3 lectures, I'm happy to discuss. So, there is actually a lot of detailed analysis one needs to do theoretically as well as experimentally. That would need a proper focused, special set of lectures on that, which would involve a lot of math.